this? Oh, okay. Yeah, there really is like no way to get rid of this glare. Whatever, it's like right there. So I won't write right there. I think
When you filmed on that one the other week.
yeah, that was much better.
Oh, it was worse.
Oh,
I saw a whole lot of light.
Oh, I didn't even notice. And on the thing, it looked better, but I was thinking of going on there, but it's a little small and there's no room. But like, because I'm standing. Anyway, it's fine. You can figure out what I wrote. But anyway, so okay, I wrote that because I didn't want to forget. Someone asked me about this. Actually, it's probably right what the glare is. Yeah. First thing I write. So someone asked me if this was true. I'm just going to copy that so it's on the video. If the real part of this, so we already know what this is by the Euler formula, right? We can do things with that. We can, well, I can talk about it in a second. But someone asked if this was true. If it was just equal to that because there's an I in there. Why don't you just take the I out or something? So this is not true at all. But it's very tempting because it seems like, or it seems like, oh, maybe it's like e to the 0 because you take the, I don't know, whatever. None of that is right. I'm clarifying because it's very tempting because it sounds like, oh, well, the real part of something, if you have x plus iy, the real part of this is x. This is exactly right always. Just say. And then the imaginary part, and we don't normally care about the imaginary part because you can pretty much always write things to only use the real part. So that's true. So these are the definitions, right? You can, what I was saying, basically you could sort of always define things to be always using the real part. Because like, for example, if you wanted to get y out of this, you could just multiply this whole thing by minus I, and then take the real part of that, and it would be y. Right? So if you take this thing times minus I, right, then you get minus ix plus y, and then the real part of this is y. So all I'm saying is that if either part you want to get, they pretty much you only ever see real, because this is physics class, and you don't really ever. I mean, so this number and this number are both real. Y is a real number. Iy is an imaginary number. But in general, in physics, we care about the real parts of things because we kind of usually it's like we take a system and make it complex which actually enhances the function. So it's not just a function of a real variable to real variable, it's a function from complex variable to a complex variable. And that actually it's actually more has more things in it. But then the real part is the only part we actually care about the whole time. It's just easier to write things in this form. But anyway, so generally we only care about the real part. So that's just a clarification about the real part. So to get what this is actually equal to, of course, we have to somehow break it up into x plus iy. But it's not obvious at all, unless of course you know how to do it, what this is going to be in real and imaginary part. It looks just like some weird function. But of course, we know that this is, I should keep the real. This is real part of, and then cosine phi plus I sine phi. So we have to know the Euler formula or whatever to break this up at all. Otherwise, this is completely, impenetrable. We have no way of figuring out what this is. And then, of course, the real part of this is, well, now it's x plus iy, where we just take cosine. So that's it. So this is real part of e phi is cosine phi exactly. This isn't like an approximation. This isn't like an ignoring something. This is literally exactly a true statement. Same thing with the imaginary part. But again, we don't, like if we wanted to get sine theta out of something, we could of course always put a plus phi plus pi over 2 or whatever, right? And then this would be cosine phi plus pi over 2, which is sine phi. It might be a minus sign. I know. Every time I write this, I don't remember if it's a minus sign. I've stopped trying to remember. So it's plus or minus. You can look it up. It's whatever. It's because the other one is going to be minus sign, so I don't really care either way. But anyway, basically the point is that we can just always use real part of this, and we get some kind of wave, and we can get any wave we want using that. And that's why this with I times anything, and now they of course use kx and they use all those things. This can actually get you any type of wave you want, right? Oscillating however you want. Okay, and now the way they write it for, so now I'll just say the way they write it for sorry, I erased it, but the way you care about it for waves is d prime. Yeah, prime. I'm just copying. This is from his PowerPoint. I kx minus omega t, and this is moving to the right or whatever. And this is on the homework last week where they take the phase and sort of absorb it into this d, and so d prime is actually d e to the I. He uses delta, which is delta is just a phase. So
Wasn't it like the absolute value of d times?
Oh yes. Well,
Like what does
yeah.
that mean?
so he wrote. I could actually write it
Is it
again.
just like the magnitude?
Yeah. So d prime is a complex number. D is a real number. This is the amplitude, right?
Okay.
The absolute value or the modulus, sometimes they call it, of a complex number is just the length. It's like because complex numbers are like in this plane of like x plus iy, right? So this is like the y and this is the x.
Mhm.
And so the length of this vector is called the modulus.
Okay.
And a phase, e to the I anything, the length of this is exactly 1. So in other words, this complex number is some real number amplitude, but then the sort of, instead of being like a real number on the complex plane, is actually a vector like that on the real line. And if you're just allowed to rotate it to any angle you want, this angle is this delta. And so it doesn't change the length at all though.
Okay.
So that's another reason why you can still, like, you might think, why would you absorb the phase into the amplitude? Like, it seems like those don't really have anything to do with each other. And that's true, they don't, but if you're going to make a complex wave function, or a wave,
Because
I guess
you
I
need
should
the
say.
phase in there, right?
You need the phase, and they like to, because it doesn't actually have anything to do with the dynamics, so they keep dynamics in here. And here is like, well, you might as well just take this real number and just multiply it by, just give it like some kind of angle. So it's sort of like the amplitude
Okay.
is now a real number just at some angle in the complex plane. Right? So in some sense it is kind of arbitrary that you're just combining these two sort of random things together. But it does make sense because this still has the modulus of this thing is still, the absolute value of this is still the amplitude d.
So the d prime is the vector,
D prime,
The
yes, d
angle.
prime is the complex vector.
and the absolute value of d prime is the length.
The length, which is the amplitude d. And the
Okay.
angle, so it's kind of like, this is in polar coordinates kind of thing in the complex plane, where
Yeah.
the d e to the I, this looks like the polar version, so this is, and so this is the this is really the amplitude, it's a real number, right? And this is the phase. And the phase doesn't change the length of this thing, so that's why it's kind of okay. Because if you were really changing the amplitude number by, like, if you were scaling it, then you'd be like, well, it's not the amplitude anymore because it's just another number. Like, that would be kind of messing things up. But if we just change it by a phase, we're actually kind of preserving it. It's just now a complex amplitude that has two pieces of information in it, which makes sense because complex numbers has two pieces of information in them, right? X and Y. That's x plus y, or r e to the I theta for r and theta. So anyway, so it kind of makes sense because it's sort of a two-dimensional number now. One of them is like the mod. Anyway, so you could think about it more and sort of philosophize about it if you'd like. But anyway, so that's why they write it like this. So this was on the last homework. They wanted you to like figure out that was
Yeah,
where the
that
phase
didn't-
went. Yeah,
That
'cause
wasn't clear, so.
no, it wasn't.
Yeah.
And they sort of should just tell you the answer at some point because if you didn't understand that
You'd
question,
just
then,
be like, what?
right, then
Which
you,
we were.
you sort of need to
Yeah,
know.
that's where we were. We were like, what?
So right, so
We were like,
that,
do we
that's
just plug in numbers?
So I was like, what do you do with this?
essentially you just plug it in and see that happened, but they don't really give you a good reason.
Yeah.
Which I mean, I guess I didn't really either, but like hopefully that's sort of
Yeah.
you can visualize that
Yeah.
that's what they're doing. They're just taking now it's automatically a vector. If we put anything inside the real, it means it can be complex. So it's automatically a vector in the complex plane. You might as well rotate it. You're allowed to rotate things. So anyway.
Really cool.
So this is just any wave.
It's just, yeah.
So yeah. So for let's say this is a length L away, this is 0, and this is in the x direction. So we're doing, again, these are all one-dimensional. I'm not going to do any three-dimensional. We could do three-dimensional, which he actually talked about a little bit with the Laplacian, which I can talk about later. I'm not going to make a big deal of it.
I don't
Um,
remember.
Okay, so if we have like two, so these, let's say these are boundaries, and so I'll just erase the. I'll make it like look like a boundary. So this is still the x-axis, but, and we have like a thing, like a string tied to the ends, right? And then we have two waves. We have let's say we have a wave going this way. Now it's described by this. Then it gets reflected, and the wave goes back from this endpoint. It's fixed here, so it's not like, you know, I don't know, it's fixed, so it has to be reflected. You saw the little animation. It's like you can see by the way that the endpoint is fixed, like the sort of forces holding it fixed, automatically give you another wave backwards. So it's a reflection, and you sort of can see that it must be a sort of a negative reflection. Like that's just how. These are all just like this is how it works. So you couldn't. I mean, I suppose you could derive this at some point, but so they give you that d incident is minus d of the reflected. So d is just, I'm talking about, this is the real amplitude now. So basically it's just the same wave, but it's going the other direction. So the incident wave is going to be called d incident times e to the I, and then we'll ignore the phase. I mean, you could actually, we should really say this, I guess. So again, the phase is going to get absorbed. It's actually not going to matter at the end. You'll see, but kx minus omega t. Okay, so here we have the incident wave, and the reflected wave. So the reason why are we reflecting waves at all? I should start with that. Well, because to get a standing wave, you're never going to get a standing wave, which is sort of interesting. I guess that's the reason. It's because it's interesting to get standing waves, because they happen in real life and they produce sounds. So to get a standing wave, you can't just have like a standing wave go, like standing waves are two waves going in opposite directions interfering in a way that does something, because of course a standing wave is not traveling right or left, and so these types of waves do travel right or left, so we would need to like add something to it. So the reflected wave, so we showed the incident wave. Now the reflected wave is dereflected, e to the I. Now the only difference we can write here is, of course, it has to be going in the other direction. So the reflected wave is going to the left, and the incident wave is going to the right. And then we can use this relation. We can use the fact that whenever you reflect a wave, like on a string, or just, I mean, anywhere, this is always true. The amplitude when it gets sent back it's just sort of the mirror image. If you sent like a pulse, like in that animation, a pulse going like this that was traveling this way, when it gets reflected, it's going to look like that. And then it gets reflected again, it's going to go at the positive. So the reflected wave also has a negative amplitude, and so we can just replace this with minus d incident. Right, I'm just using a little bit, I'm just plugging in this relation. Again, I'm sort of forgetting about the phase here. You'll see again that it doesn't actually matter. So I guess I could put absolute values and put a phase here, and then anyway. So, but then the total wave looks like what? Well, now if we actually want to plot y of x is the literal. This is y. This is y of x, right? If we want to actually plot y of x and t, I should say, and t. Well, what does it look like? I mean, we have these two waves, but these waves are not. They're happening together. So y of x is just the sum of all the waves on it, right? So like, that's kind of how we normally do things, like the sum of the forces. We just take the sum of all the waves on it, and we get, well, it's clearly d incident e to the, well, anyway, you'll see. It's this plus this, right? I'll skip a step by factoring out a d incident, because we know this is the same. So we get e to the I kx minus omega t minus e to the I kx plus omega t. So of course, if we factor out a d incident, we get a minus sign here, which is important. We can actually also factor out a e to the I kx, right? So if we write that, we could write this as d incident, which is just a real number, or I guess complex number. E to the I kx, that's the same in all these, right? Times, and we get e to the minus I omega t minus e to the I omega t. All right, does that make sense how I'm factoring this? Because of course, if you add things in the exponential, like e to the a plus b is just e to the a times e to the b. So I'm just sort of, if you distribute this, you'll see it's identical to that. But now, so now we have this. This is interesting. Now we have this thing here, and so if you haven't seen it before, it seems like who cares? But this is identical to 2I sine omega t. And the reason, so this is d incident e to the ikx times 2I sine omega t, and it's because there's some identities. I mean, you should look these up rather than trust me because I'm probably going to get them wrong, but it's like there's some identities like cosine of theta is e to the I theta plus e to the minus I theta over 2, and sine theta is e to the I minus I theta minus e to the I theta over 2I. So it's something like this. I might be off by a sign. I'm not off by more than a sign, I think. But anyway, there's some identities like this that you can look on, that they're sort of non-obvious. Yeah, which is actually, well, okay, I won't say it. There's some interesting things you could say about this, but I won't say them. Yeah, so anyway, so what's interesting is that we get the spatial part and the time part are now separate. So remember, like, well, there was some, I said it one time in office hours, I don't remember what I was talking about, but there was, you could write the spatial component and the time component as separate, like sine, you could write sine kx times sine omega t. And that's kind of more clear what it is because there's like clearly a separation of things. But we tend not to write them like that because that's not really like easily, well, then you can't really see how exactly they're tied together. But in this case, we see that we actually do get this separate, we get just a e to the ikx, which looks like a wave. Like the time and space components are completely independent, basically is what I'm trying to say. And this shows that we have some kind of, like, actually, how does he write it? Well, okay, sorry, I forgot the real. Sorry, all these have a real. Right, that's what I'm forgetting. So therefore, this, yeah, okay. I was like, how am I going to write this? So this, it's really the real part of all this thing. So d incident is still real. E to the ikx, of course, the real part is just cosine of kx, right? And the other part is, oh, actually, sorry, we have an I. Oh, yeah. Wait a minute, how do I get rid of this I? Yeah, 2I, yep, that's what I have. Oh, I see. Well, they did something. So the note, the PowerPoint factors out the other thing, factors out the omega t. It's the same. It doesn't matter. But I'm trying to figure out where this I goes. Oh, sorry. This is so he made a point. Yeah, that's right. This is kind of subtle. So he made a point about this. This I. So we can't. Okay. So it's the real part of this whole thing. And again, we're just trying to do standing waves. We're just trying to get the function for a standing wave, right, on a string. Now you might think, oh, we have a big number, but there's an I in the middle, and we're taking the real part of it. So isn't it just like, well, it's something times I, so shouldn't this whole thing just be 0? Because if we're taking if we take the real part of I, z, right, isn't this just 0 because there's no real part? Well, no, because of this thing here. So the fact that there's an e to the ikx, so sorry, I should have erased this. I wasn't ready to do this yet. Because there's an e to the ikx, this number sometimes is real and sometimes is imaginary, right? This is not always one type of number. So therefore, we actually don't know much about this whole thing. So we have to replace this I with its exponential form to combine with this. So I is equal to, so have you seen this before? So he mentioned this quickly yesterday, but so remember if we draw the complex plane, right, then 1 is like this, if this is the real axis and this is the imaginary axis. 1 is like this, minus 1 is like that, right? I is like that, and minus I is like that, right? So this is I, minus 1, 1. And all I'm doing is writing it in polar coordinates, right? So in the complex plane, of just like any plane, we could write it in polar coordinates. 1 in polar coordinates is just 1. That's fine, because there's no angle. I in polar coordinates is 1, which is the magnitude, times e to the I theta, where theta is a quarter of a rotation, which is pi over 2, right? So this. Minus 1 is, magnitude is 1, the times e to the I theta, where theta is now this whole thing. So this is e to the I pi, which is this half rotation, right? A minus I is, 1, still magnitude is still 1 times e to the I 3 pi over 2. And then we could write 1 again as 1 times e to the I 2 pi, but of course, that's another identity we could write. 1 is e to the I 2 pi. This is also true, you could always replace it. Because it's sort of cyclic, you could go around. Anyway, so this is a bunch of stuff. The point of this is that we want to use this identity, which is just, again, it's all I'm doing is rewriting. They're identical symbols. This is in Cartesian coordinates, I guess you could call it. This is in polar coordinates. That's the only difference. This is not a special rule or anything. This is literally just a changing of what sort of I'm calling my coordinates. And so then you plug that in here and you get e to the I kx plus, so I'll put it in parentheses, plus pi over 2. And now I can definitely write this. Now I have e to the I. This is real. Sine of something is real. There's no imaginary things here. 2 is real. D is, well, let's say D is real. This is just now this real part of this thing is just now cosine of that. So we get equals D, incident, I suppose, cosine of kx plus pi over 2 times sine, there's a 2 somewhere. Sort of don't really care about the 2. So there we go.
The 2's like multiplied by the.
Yeah. Sorry, it should be like 2.
So it's like 2D.
Yes, yeah. I just forgot it when I wrote 2D incident. Yeah, and so that's exactly what he has here, except of course in his, in his it's a little different. So he does the sort of the whole thing, but puts the pi over 2 on the other thing. It doesn't really matter. It's actually just a change of phase. Anyway. Okay, I kind of wish I did that because it's going to be a little easier, but. And then, then I'll just talk about, real quick about sort of, I kind of want to call it quantization, but I don't want to make it sound harder than it is. Quantization means that if you have a standing wave that goes over a length L, which is sort of what I meant, I just erased the thing, over a length L, and it's described by just sine of kx, let's say, for example. Let's use sine of kx. Actually, sorry, I should have done, so I kind of messed up a little bit. I didn't mess up, this is still right, I just, by a change of phase, I could put this pi over 2 on this term. Just back here somewhere, I would just change my phase, absorb a phase into here, and like shift everything over a little bit, and I can make this a sine of kx, which is kind of what I want to do because it's just much easier to describe standing waves. Because at x equals 0, if we have like a wire that we're vibrating, or like a string or whatever, or a string on like an instrument,
So it'd be sine of kx times cosine wt plus pi over 2.
Yes, what you said is exactly what's in the notes.
Okay.
So if you use the notes, please if you use the notes, it's the same derivation. It's just that he sort of was a little more thoughtful than me and put the pi over 2 in the right place. Now this is still true. As I said with the original equation that I erased, of course you could describe any wave with any of these. So this is not a wrong answer at all. It's just not as easy as I thought it was going to be. So it's not a wrong answer because of course we would just have to be careful about that. This is a better answer because at x equals 0, we already get that this is always equal to 0. That's not an extra condition. It comes automatically with sine, right? So this is sort of, I'll call it's quantization is what it's going to be, but you'll see why that's not as hard as it sounds. So what we want to do is say that if we just write sine of something, it's just some wave, and depending on what we put in there, it's just a wave with different wavelength, and frequency, and all that stuff. But we want only the waves that they have to start being 0 at 0, first of all. That's all automatically. And they have to end at x equals L, they have to be 0, right? So y is the function of x, by the way. So at x equals L, y has to be 0, right? And at x equals 0, of course, y is 0. These are boundary conditions, but it's just a requirement because if we like write a wave that doesn't have this property, it can't possibly exist on a wire. That's the ends are fixed, because the ends being fixed are, we force that to be the case. So like, so we have to so this automatically gives us its first condition. That's the only reason why it's better than this condition, because this we'd actually have to impose that and we'd get a condition on x, which would be fine. It would just not be as nice. This is automatically implies this. That's fine. But we also want to say that y of L has to be 0, right? Which is this. So we get sine of k L has to be 0. Now we get, okay, well, KL is a number, right? It's not there's no variables in here anymore, it's just a number. But sine of some number is only 0 if that number is what? Well, it has to be, there's only things that when you take the sine of you get 0 are things of the form n pi. That's just you could try it. There's no, all of the, so it's important that this is very crucial. Like you can't, if you said 2n pi, you'd be right that 2n pi is always 0. Sine of 2n pi is always 0 for all n, but you'd be missing some of them, right? But in this case, this is actually all of them. Every time, there's no, all zeros of sine is sort of what you call it, have the argument be something like n pi, where n is an integer. I'll write the funny little thing. This means an element of the integers. Z is the integer in like German or something. So anyway, I forgot I don't know how to speak German. But anyway, there's a thing, you can look it up if you want. But anyway, so this means an integer. It's positive or negative and 0 is totally fine because sine of 0 is still 0. So, but this is actually a very specific condition because this relates. Now these are all just fixed things. None of these are variables, right? There's no condition on x here. This literally just says that, well, I guess k, assuming we have a fixed L, k can't just be any number. K has to be n pi over L. And pi over L is just a number again. This is just this could be 1 meter, whatever, it's a length. Pi is a constant, obviously. N, therefore, it just takes that fixed number and says that any multiple of that is an allowed value of k, but any other values of k, all other real numbers, will not satisfy this equation, which means they can't describe the wave here. So so I just took a small piece of this equation and solved for it, which is the part where basically it involves setting this to be 0 at x equals 0 and x equals L. And if we do the phase thing and replace this with sine, it would be exactly that. This part sort of cancels because it has no x's in it, so we don't care about it. Like it doesn't, for now, like this has to be, sorry, I should say at t equals 0, let's say. So if we plug in t equals 0, this term goes away automatically. Well, actually, then the whole thing's 0. Sorry, at t equals anything. Right, at all times, that has to be the case. It has to be fixed at the endpoints at all times, meaning we can ignore this term because this could be anything. So we would need this term to go to 0 to get the whole thing to be 0. Right, we can't count on this being 0. Because at some times, the whole thing might be 0, right? There's some times it's when omega t is n pi. But we don't want to give restrictions on times because that sort of ruins the whole thing. It's supposed to be allowed to evolve in time. Anyway, so this is called a quantization condition. Quantization just means that you have something that can be an integer copy of something. Basically it means that k can't be any real number. Like before, like k was, well, k is like a wave number. And I guess you could relate it to a wavelength before in the harmonic oscillator. Actually, we didn't use k. But anyway, you could imagine like things like the mass, and most parameters we give it can be any real number. There's no rules about it. But in this case, we actually get that it can only be an integer copy of some fixed number, which is given by the, external, well, the length of the system or whatever. And so, and so now I'm going to erase this. So this is how we get this quantization condition, and so what do I want to say? So if we actually plot this first, so if we plot sine of n pi x over L, if we plot this for n equals, well, if we plot this for n equals 0, so this is y of x. Now, of course, if for a wave, it should also be a function of time, and we see that there's this other cosine or whatever of omega t. But of course, we're like picking, let's say we can pick t equals 0 then. If I put cosine omega t, we pick t equals 0, and that term goes away. Because again, for standing waves, they should be standing for all time. We shouldn't have to care, they have the same fixed endpoints at all times, so that doesn't really matter. So if we take the spatial part, then if n equals 0, we get a flat thing. We don't even call that a wave. I mean, it is technically a wave because it solves the wave equation. That's the definition. So it is a wave, it's just not very interesting. For n equals 1, that's the lowest number. Like, forget about the negatives. Negatives are fine. It's just that sine of a negative number is negative sine of a number, right? Because it's an odd function. And then we just get, because it's standing, it sort of oscillates up and down, so it sort of seems like the same thing. So we don't really care about negatives, but they really exist. But for n equals 1, we get something like this. Okay? That would be the plot. It would look like, because at x equals L, right? Well, that's sort of obvious. We already know at x equals L, it gives 0. But basically at x equals L, it gives 1 times pi, which is, of course, when we plot sine of pi is 0, but it's the first time it gets to 0. There's no zeros in between 0 and pi for sine.
So if it was like n equals 2, there'd be 2.
Exactly. So
0.
exactly, because for n equals 2, then at the end point at L, we get L over x equals L, we get 2 pi. But of course, at sine of 2 pi, there's a point in between sine of pi where it's 0, halfway, of course. And so we actually get that. Right? So it seems, obviously, it sounds complicated, and then I'm drawing something like really simple, but it is kind of complicated to imagine. But it's really just this equation, right? It's just this exact equation. So usually they draw both because again, it's a standing wave, and so at t equals 0, it literally looks like this, right? But if you evolve over time, it should sort of oscillate, and this point should always be 0 because, again, the full wave function looks like this. I'm switching again. I apologize. I'm switching to his notation, which is, again, it's the same, but it's phase shift. There's an amplitude. No one cares about that. So this means at t equals 0, this term goes to 1, but at all times, this at x equals L over 2, let's say. If we plug in L over 2, we get sine of 2 and 2 pi over 2, which is sine of pi, which is 0. So that's this point is 0 at all times. It doesn't matter what this is. If sine goes to 0, this whole thing goes to 0. Right? So that's kind of the point, is that at all times this is true. If we find order at this point, which is going to be it's going to be L over 4, right? And if we plug in L over 4, we can see that at time 0 we get sine of pi over 2, which is 1, right? And then if we, of course, if this is 1, this could give us 0 at some times too, because this could go to 0. But that's fine, because it just means that the sort of string is going up and down. Of course, it passes through 0. It does all the values. So, so it's kind of, you have to keep in mind these two things. For the most part, the advantage to using sine for the spatial part and cosine for the time part is that at t equals 0, this goes to 1, which is what usually you want. And at x equals 0, this is 0, which is also what you usually want. So it's just a convenient, again, sine, cosine are just related by phase shifts. You could always change them, but that's why the choice he made in the notes is more convenient than the one I made. And then at n equals 3, let's just try equals 3. Well, we know we should get, I mean, you can kind of see what's going to happen. This means that we get 3 pi is when it goes to 0 here, but that just sort of means that you have something like this. And that means, so in this one we have one node. Well, it depends if you want to count the endpoints as nodes. Let's say no, we don't want to do that. So, and n equals 3 has two nodes. Okay, but so what about the wavelength in all of these? So the wavelength is going to be, well, we can kind of see what it is. I mean, in this case, the wavelength is this whole thing. The wavelength is when it goes through one sine wave, right? The distance it goes through one sine wave. So in this case, we have lambda equals L, right? Lambda is the wavelength, right? In this case, we know that lambda, the wavelength, is actually 2L, right? Because it only has half of a wavelength here. And here we know the wavelength is, well, it's like 2/3 of L, right? And, well, it's a little hard to see now. But if you go to the other way where you say let's say L is, so here. Let's call this 3, 2, 1. And let's say, where do I want to say? L is lambda 1 over 2, which is also lambda 2, okay, which is also 3 lambda 3 over 2.
Wait, so,
Uh-huh.
like the top one?
Yeah.
Isn't it like half of the sine? Like function? Why is it 2L? If the
You're only getting half of the function and one of L. So you need to do it twice to get the other half.
Yeah, I was gonna say, just manipulate the equation. Lambda over 2, 2
L
over
equals half lambda.
lambda, yeah, half lambda, thank you, equals L.
Yeah.
Thank you.
Yeah, so L, another way to say it is L is half of a wavelength.
okay.
So L is lambda 1 over 2. I really should have written it like that. Sorry. This is much more obvious to write it. That's why, okay, let me put that
I
here.
was seeing that last one as 3 lambda over 2, and then you wrote 2.
Yeah, exactly.
L. I'm like,
2/3 is a
alright,
weird,
That's fine.
if you get 2/3 it's weird. 3/2 is fine. Because, well, you'll see. But yeah, this is a much more intuitive way to write it because we could just writing L, which is this length, right? How much of a wavelength is it? This is exactly a wavelength. This is half a wavelength. This is 3/2 of a wavelength.
Okay.
Yeah, sorry, I should have written like this is how they normally write it, and also the pattern works this way. It actually doesn't work, well, it works, but it's not as obvious the other way. And you can see I'll just draw n equals 4, even though we sort of know what it's going to look like. This should be 2 wavelengths. And I'm going to write that as 4 halves for a reason that should be obvious now if I write this as 2 halves. So you can see that n is, this is n equals 4. Then right, and then we can write sort of something like L is n lambda over 2. Right? So so the relationship between if you needed to find, let's say, the wavelength, I guess that's kind of a weird thing to find. I guess that's fine. You could also just say 2L over lambda. 2L over n is lambda n. Anyway, this would be the wavelength of if you have a piece of string of length L with fixed at both ends, and you needed to find the wavelengths of the nth harmonic, you would get this. So this is, now you shouldn't memorize this. Well, I guess you could memorize. Well, no, you shouldn't memorize it because it's like you can kind of draw some pictures, right? This one is much more easy to visualize, but this might be more useful. But you should be able to find it online, somewhere. But so that's important. But of course, the more important part, not the more important part, slightly less important. But also, they might ask you about is the frequency of all these things. So all these things have a frequency, of course, but
Just manipulating lambda equals 2 pi f.
lambda equals 2 pi f.
That's something, isn't that?
No, it's something like that.
Okay.
That's not that, but you're right. It's just so it's something basically. Okay. Sorry. then it would just be manipulating this type of
Oh,
equation.
that's what I was.
So v is right. So v is the speed, is the velocity of the wave. And this, by the way, means so these are all standing waves. So what is the actual velocity? Well, remember this, as we just saw, the standing wave is actually made of two waves going in opposite directions, right? So velocity is actually the velocity of the waves going in different directions. You can't actually see if you're watching a standing wave. It's not obvious what the velocity is, right? Because you can't actually see both waves separate, but you know they're there. So that's the velocity. But that also relates. Now lambda is in meters and frequency is in 1/2 So this is in meters per second. So this is the relation between them. And if you knew the velocity, then of course you could just find, it would just be frequency of the nth harmonic is just the velocity over lambda n. And now the velocity though is of course given, depending on what it is, given by like the tension and the what is it, tension and the linear mass density or something. They won't usually ask you about those things, but if you knew so you'd have to find the velocity another way. I mean, if you knew both of these, you could find the velocity. So if they ask you what the velocity is and they give you these for the same harmonic, of course they can't give it to you. They can't give you lambda. I mean, they could, and then you'd have to do some more work. But what I mean is you can't multiply if they give you the wavelength for the second harmonic or whatever times the frequency for the first harmonic or whatever. You can't just multiply those. You have to multiply them for the same one, and you could convert between them, of course, if you just knew what they looked like. So if they tell you the length is this, and I don't know, you could piece together these things written to solve different types of problems. I don't know. I'm not gonna think of a good example, but I just mean like if they tell you the third harmonic wavelength, you could use this to find the length, and then use the length to find whatever else you need. I don't know, but just it's important that these are the same. These are at the same point. The velocity is not just any wavelength times any frequency. It's specifically for the same harmonic n. Does that make sense?
A lot more sense than it did yesterday.
Yeah. Okay. So actually, but then I wanted to. So I don't know. Did he talk about if they were both open, if both ends were open? He mentioned a flute, which is if that's true for a flute. I don't know if he.
I said
I
we
don't
would
know.
get to that.
He said he wouldn't get to that.
No, I thought he said we will get to that.
Oh.
I don't think you went over it yesterday. He said something about like woodwind and.
Yeah, he's talking about woodwind. Well, okay. I'll just say real quick.
Got to a point.
If both ends are open, it's actually identical, because then what you're just saying is that so an antinode is the opposite of a node when it's like maximal. So if you say both endpoints have to be antinodes, then you could just write like it looks like this. This is n equals 1. Well, again, n equals 0 is just where it's open the whole time. So you get this. Well, this should be dotted, I guess, if I'm using the same. That's n equals 1, and n equals 2, it looks like this, but both ends are open. It's actually exactly the same, though. It's the same, all these are the same. Because, well, it's sort of by symmetry, you could just say, why don't I just shift this over? It'll actually always be the same as those. So if they're both open, that you could treat it as the same. You could actually, there's a physics way to interpret it as the same, where, like if you have a flute where both ends are open, depending on if you're talking about if you're plotting the actual pressure or if you're plotting the velocity of the air, you can actually kind of convert between closed and open. Anyway, it's a long story. It's not very interesting, but it's in principle it's the same thing. There's another one, a third one, which is actually not the same, which has different values. So this formula is not true for the third one, which is called closed open.
One end fixed.
Exactly. How did you?
I
So
remember this from vibrations.
yes. So this one is actually kind of annoying
Terrifying.
because there's sort of a weird odd number.
I'm terrified and I haven't even heard of it.
So closed open just means so. Again, I don't.
come into this terrified. I don't.
I don't know for this. This is the reason I actually said not to memorize this, because of the closed open has a different formula, and if you just remember this, you'll get it confused. The thing is, I don't know if I'll ever ask you because it's not actually interesting.
What was the antinode wave called?
Open, open.
Open, open.
Well, I just mean like those are boundary conditions.
Okay,
So closed,
okay.
closed is like a string.
Mhm.
Open, open's like a flute. I think. I've never actually really seen a flute, but
It's open.
it's open, open. Which means that the endpoints, so the boundary conditions at the endpoints have to be antinodes. And of course, by sort of symmetry, you can kind of see that they're all going to look the same. Maybe the function is going to be slightly different, but the relation between these two, like how many wavelengths does it take, it's going to be the same fractions, right? You're going to have, a full wavelength either can look like this or it can look like this. Right? This is an open, open, n equals 2. Right, and you can see it's literally just this, but shifted over. So all these formulas are identical for open, open, yeah. But for closed open, that means that you have, now this is some instruments, there's some, I assume, woodwind type instruments where, I don't know any examples, but one end is closed and one end is open. Which means that the boundary condition is that this end has to be an antinode and this end has to be a node. And in that case, well, the n equals 1, the lowest, actually, I guess it might even be n, well, no, it won't be 0, but it'll be, n equals 1 will be like this. And this is actually lambda, this is lambda over 4 is L. Right, because you would need 4 lengths to make a wavelength, right? Because this is like a quarter, this is like half of this. Right, but it's not, and you might think, oh, that's easy, it's just half of these ones. No, it's not, because if you double this, you'll get this, but this is not closed open. Now this isn't either, but if you did something like this, oh, sorry, I already messed it up. Like that, this is n equals 2. And now what is this? Well, this is actually 3/4 of a wavelength, right? 3/4 of a wavelength is L. So now, the actual expression, and you can keep going, it's just, one more thing. It's actually, let's see. See if I can do this. I think it's 2n minus 1 over 4 lambda. Right, 2n minus 1 is, if n equals 1, it's 1. If n equals 2, it's 3. Yeah, so this is remember we used this thing for the sign, and right, the Taylor expansion, right? This means odd numbers, just in case this comes in handy a lot. 2n, of course, is even numbers. That's easy, but 2n minus 1 just gives you really odd numbers. So anyway, it's this, and there's a 4, which is kind of annoying. But anyway, that's the thing. This is for closed open. Again, this relationship, of course, is still true. So, but the frequencies, again, so you can convert this if you know well, I guess we could convert it right now. This implies that Fn is NV over 2L. Right? All I did was plug in this, so I should write like a, sorry about all these arrows. They're supposed to sort of mean that's how you get places. Anyway, hopefully that makes sense. But so all I did was plug in, hopefully correctly. Yeah, plug in this, and so you get now the frequencies, of course, are inversely proportional to the length, and of course proportional to the velocity. And they actually increase linearly with n. That's actually kind of interesting. So the frequency, so this is actually why the musical instrument, that's the whole thing which I went, that's why they work, because you might think, well, these have this weird, yeah, okay, that's fine. That just means that like n equals 1, n equals 2, n equals 3, they're just, all you're doing is getting copies of this quantity, v over 2L, which is just a fixed constant. And if you increase n, the frequency, which is actually what you hear, you don't hear the wavelengths, of course, you hear the frequency, you're getting multiples of that frequency. So the fundamental frequency is this thing. Right, is the n equals 1, which is if you plug in n equals 1, you get this v over 2L. This is the fundamental frequency. And as n increases, you get, they call the harmonics. I've never actually seen, they don't have so he made several mistakes in class describing, not mistakes, but just inconsistencies, let's just call that, describing what the harmonics were, how you label them. So I'm not even going to try. Generally, the fundamental, that when they say harmonics, they mean the ones where n is greater than 1, n is 2 or greater. I'm not going to say that, so sometimes they say n equals 2 is called the first harmonic, and n equals 3 is the second harmonic. But sometimes they say n equals 1 is called the first harmonic, and n equals 2 is the second harmonic, which makes sense. None of those are all useless pieces. Like, those are ambiguous. So if they should just tell you. So don't worry, if they give you this, if you can you should be able to see what n is. Because you can see by just counting. If you didn't know for sure this was 3, because you're like, I don't know, well, it looks like 3, but like, the numbers are all weird, so I don't know. You could just count the ones that are below it, and of course, well, this must be the lowest. I cannot possibly make a lower one, so it must be 1. This is the next one, 2, and then I get this 3. So you can count that it's 3, and then you could do whatever you want. Don't worry about the names harmonics, the first, second harmonic, I don't know, whatever. It just means, if they say it, you can always ask on a test. You could always ask him, what do you mean? What are you counting from? Because it's not obvious, and I don't know what his slides say and what he said. I don't think they agree. But anyway, so does everything make sense here?
Yeah.
Okay. So I won't talk. And then again, this is just, you could of course convert this to a frequency by inverting it and putting over v. You just get some weird thing with 4, and don't worry about it. If you need it, you could always. They'll probably. Well, I don't even think it's on homework, so don't worry about it. It's the same principle. There's nothing actually new about it. It's weird formulas. So, these are the important ones because you can draw them very easily. And, Okay. There was another thing. Oh, okay. Beats. Someone want to talk about beats? No one sounds excited.
Really.
Do you know what beats are?
No.
'Cause he said, he had a thing about them.
Is it like the square wave thing? No, that's not it. But like
No,
I
that's
got
cool too.
nothing out of his
yeah, no.
brief
So-
discussion.
You said beats, and I automatically thought The Office, so that's where my mind.
Bears. Battlestar Galactica. So,
Yeah, 100%. That's what I
yes.
thought.
2 waves out of phase that every so often you hear
yes.
magnification when
Yep.
they meet.
All right. Does anyone else have any questions?
That was great.
No, but that's very good. Yeah, that's right. Actually, I was going to talk about the square wave. This thing is kind of cool. You don't need it for anything, but it's kind of cool because it literally demonstrates a Fourier series. If you add up a bunch of waves with different frequencies. Anyway, I'm going to stop. I could talk about it for a long time because there's really cool things, but you don't really need any of it. So I'll just talk about beats. So let's say you have 2 waves. So of course, if we have 2 waves on the same place, well, let's just talk about time for now. Let's say you're receiving 2 waves. There's no spatial thing, it's traveling, whatever. We're just care about at one point, it's just a function of time. And let's say you get some amplitude, I don't care what the amplitude, e to the I omega 1 t, plus e to the I omega 2 t. So what this is describing, and there's, of course, there could be phases, there could be amplitudes. I'm taking all those unimportant things out. This is describing you're hearing 2 waves with different frequencies. Okay, of course they could be the same. We could set that equal at the end. But for now, the 2 frequencies, omega 1 and omega 2, and of course, if we wanted to convert them to like that, right? We could convert them to actual like hearing frequencies in hertz if we wanted, but who cares? So then, one thing we could do to get this to look nicer, to hear 1 wave, because of course when we hear something, we actually hear exactly 1 wave. You don't hear 2 waves, right? Because your eardrum has to move. If you just plot where your eardrum goes, it's not going to go in 2 places at the same time, right? It goes in 1 place. So this can be written as a single wave. We know that, of course. Every wave can be written as a single wave, every sum of waves, because it's, the mathematical reason is because they solve the wave equation, which is a linear equation, if you really want to know all that stuff. But anyway, so what we could do is say this is equal to we could factor out something because we know that we could, if we get something like this, e to the I theta for some number theta, plus, okay, make sure the sign right, e to the minus I theta, we know that this is 2 cosine theta, right? This was from our identity before. So once we get something like this, we can have this. Now, this is actually, this is not automatically this form because these are not the same. But if they're just 2 numbers, what if we factor out something and such that those two are the same? I mean, they're just 2 numbers. What if we factor out something that was right in the middle of them? And then we get, like, let's say omega bar, which is usually means average, right, is omega 1 plus omega 2 over 2. If we factor out e to the I omega bar t, okay, we get e to the I, well, it'd just be omega bar minus omega 1 t plus e to the I omega bar minus omega 2 t.
Never seen it like that.
That's easier.
That's weird.
Really?
That makes. I've never seen that. No. But I understand it.
Good. Okay, that's good. Let me know if you stop because
No. Yeah.
I might make a mistake. Now, they, of course, so they use a different, in the notes, they actually start with something, they start with basically something much easier. It's, of course, I'm just trying to show that you don't have to start with anything easy. So, which may be not a good decision for me. But, okay, but now, literally omega average minus omega 1. Yeah, okay, this is fine. So what's omega average? Well, let's write it as this. Right? Omega average minus omega 1 is going to be what? Let's call it delta omega. So e to the I. I know I'm sorry about all these new symbols, but let's call omega average minus omega 1 delta omega t, okay? Plus e to the, well, now what must be omega bar minus omega 2? Well, if omega average was halfway, it's the average of those two things, so it's halfway between 1 and 2, right? That's what the average means. And so if it's halfway, that means it must be the same distance from the second one as the first one. So this number and this number must be the same, but of course one of them is greater, so this one's actually going to be in minus delta omega. Does that make sense? Now, you could write this all, it's very easy to write this all out in terms of these things. I started to do it, but you could do it. I just want to get, this is more interesting. You could, I want to show you things here that you don't just be able to write out and see, because those are sort of easy. But I want to show you, like, this is actually kind of intuitive, is that if I'm factoring out the average, I get this. I guess, I probably put my signs in the wrong place, but it doesn't really matter. It should really be omega 1 minus omega bar, I guess. But anyway, but then, of course, the average is halfway between them, and so this quantity are the same, of course, but one of them's negative, because one of them, the average is below it, and one of them, the average is above it. Right? These are true for every numbers. These don't have anything to do with the, this is just numbers. If you have 2 numbers and take the average, they have the same distance between the average and each number, but one of them is negative if you subtract in the same way. So anyway, you get something like this. Now we have this. This is exactly what we wanted, because this is just 2 cosine delta omega t. Now remember, delta omega is just it's a frequency. It's not a weird new thing. It's literally just another frequency. I just called it delta omega. And omega bar is also just another frequency. Now this is my new wave function. This is y of t. Now I've written it as a single wave, right? But of course this thing is just an oscillating wave. But we have this other thing too. And so we actually get, and remember that this number delta omega is actually, so generally in like, let's say things when you hear them, the average is going to be pretty high because, like, let's say that one of them's like 400 hertz and one of them's 500 hertz or whatever. Generally, the difference between them, this is actually half of the difference. Okay, that's fine. So delta omega, by the way, is not omega 1 minus omega 2, just so you know. It's actually half of that. Anyway, sorry, because I think in his notes it's, in his notes it's slightly different. In his notes he defines the delta omega in the PowerPoint is actually half of my delta omega, just so you know. But anyway, don't worry about that. As long as you follow this, that's fine. So then what you get is, remember when we had the damped harmonic oscillator, we got a wave that had like an oscillating part and a exponential part that decayed, and we knew that you can just take the oscillating part and like put it bounded by the decaying part. Well, now of course this is still oscillating because there's an I, so it's not quite that simple. But this oscillating part has a very high frequency because omega bar is very high. It's just it's the average of the two frequencies. But delta omega is actually very low frequency because generally this happens when they're very close together, right? You're generally in real life going to hear two frequencies that are close together. They're not going to be like really, really low and really, really high. That would be kind of weird. So if they're very close together, that means this is actually oscillating very slowly, and this is oscillating very quickly. So let's just, if we say take the real part, this is like sine of omega bar t. So there's just two oscillators. I don't care about the sine, cosine. So we actually get something like this. If we plot this cosine, we get like I don't really want to. Right? Yeah. And if we plot the other part, sine, we get, remember this is very high frequency now, because it's the average. We actually get, and now it's the same reason before we actually want the positive and negative parts, because just like remember when we bounded the other thing, the damped oscillator, we took the positive and negative because the other thing could oscillate. This is sine of omega bar t, and that of course goes between 1 and -1. So we actually get something like this, and it's high frequency, so it oscillates very quickly. Right? So somehow what we did, so what you hear is this one. You don't hear well, actually you'll see. The sound that enters the sound you hear in your ear is actually this thing, okay? But of course, if something is sort of increasing in intensity, then decreasing, and then increasing, and then decreasing, right? If something's, okay, I think this is all right. I mean, the principles of what I'm saying are right. I'm worried about this graph. This graph might be slightly wrong, but it looks just like this. It just might, I might have to do a squared thing where I worry about this. Anyway, it doesn't matter. The point is that, like I said, two waves of slightly different frequencies were emitted, and what you hear is just the sum of them. But of course, you only hear one wave. When we wrote it as one wave, we actually saw that the one wave just has a very high frequency, about the average, which is with the average of those two frequencies. That makes perfect sense, right? When you hear two waves very similar, you kind of hear the average, right? So that makes sense. But the weird part, though, is that it increases in intensity and then decreases with a sort of wavelength, or frequency, I should say, of the difference between the two frequencies. Right? Does that make sense? So if you had like, if you heard two frequencies that were like 1 hertz apart or something, then you would hear this sort of beat, right? These are called beats, right? Where they go down. So this is sort of like a wave going up and down. Now remember, you're not actually, there's nothing the wave isn't actually doing this. It's actually doing this. But of course, you can tell that it's getting louder and quieter and louder and quieter. And the frequency that it does this is this, because it's just the product of two waves. This is a very high frequency wave. This is a very low frequency wave.
Right now, I understand how we drew that. I get you now. But so the way that I originally learned it was that there were two waves traveling. You could say one was 1 hertz less than the other.
Sure.
And so you'd hear the beat frequently. You'd hear it quickly.
Yeah.
They were, 20 hertz out. You would hear it obviously slower, but it's when they're both at their peak amplitude, that you hear that.
Yeah.
Okay.
Right, and because what happens is, it's just, if you plot these two now, I mean, this is the same as if you just plotted, you could just literally graph these two and add the amplitudes together. And at some points, they would cancel out. It's actually these points.
Yeah.
And at some points, they would add up right here. So of course, if these both had amplitudes, this actually has twice the amplitude that the original had. So this height here is actually twice the initial intensity of those two waves. So when they constructively add, of course, the amplitude should be twice those amplitudes, right? But when they cancel out, of course, it can be 0. You know. Yeah, and actually the important part is, I think it's kind of what you said, which is that this delta omega is the difference between the two. If they differ by 20 hertz, let's say versus 1 hertz, so 20 hertz is kind of a lot. This is actually going to happen very quickly. So you're going to get sort of quick, quiet, loud. If they only differ by 1 hertz, this is actually going to be, this is 1, and so you're going to get a very, very slow.
Wait, I thought it was the other way around. If it was 1, you'd hear it more frequently inside of a period, right? A period, span of time.
No, if it's 1, then you're only going to hear it. If it's 1, you're only getting, so like if it's only 1 hertz, that means you have a wave that's like this.
Yep.
And a wave that's like very slightly longer, let's say. And they're only going to perfectly sync up. It's going to take a while.
Yeah.
Before they perfectly cancel out, right, like that, or perfectly add together like that.
I had it backwards. Okay.
Yeah. So that, okay, good. So these are the times when they are silent and when they add together like this. Sorry, this is like silent. This is like added together. And if they're very close to the same wavelength, then it takes forever for them to line up to do either of these things. So that means that this is going to take a while, which literally means that if omega 1 and omega 2 are very similar, delta omega is going to be very small, and this is going to be a slow oscillation. If they're very, very different in wavelength, like if one is this and one is like this, well, of course, every time this gets to low point, there's going to be some point where they sort of cancel and some point where they add up. They're far enough apart that the high frequency one sort of goes through the whole cycle at all the time. So you could always find points where they're going to add up. And so this delta omega would be very close to like this frequency maybe, which makes sense because delta omega is omega 1 minus omega 2. Maybe it's like 1/2 or whatever. Who cares? But if omega 1 is very, very small, if this is very small, like, okay, let's call this omega 2. If this is small compared to the other one, then it means it's very similar to that, and you get roughly the same beats as the high frequency one, which literally just means like there's no beats. Because you can still write it like this, of course, but you just get like, it doesn't happen it's not as pronounced. Anyway, so, okay, does that make sense? So essentially the important mathematical part is going from the sum of two waves to writing it as a single wave. That's kind of the whole thing, is when you get these waves, of course, you know that by some math things, linearity of the wave equation, I guess you could call it, you know that every solution of the wave equation can be written as a single wave. And therefore, if you add a bunch together, that's still a solution, and therefore it can be written as a single wave. It just might take some techniques. If there's a way to, this is the main technique, this thing, and then of course, if you put a minus sign, it's 2i sine, so that's the other one. But, and now you get, of course, another oscillating thing, so it's just like the product of two oscillating things.
If you add a negative in the e's.
Yeah, so e to the I theta minus e to the minus I theta. This is 2i sine theta. I think I might have the sign wrong, which just means you switch these or whatever.
Yeah.
I believe this is right though. I think I said it wrong before actually, but I think I wrote it slightly backwards. I would look it up. I would look all these up. Yeah. Okay, and I'll just say really quick about the. Is that good for everyone for the beats? Okay. I'll just say real quick about in fluids, which is not very important. Well, yeah, okay, it's not very important. It's just the wave equation. So U is the solution.
Does it cover fluid mechanics?
It's in the PowerPoint, and there's a question about the speed.
Oh, I meant like as its own subject.
Oh,
Or is it just-
I don't know.
Okay.
2i.
I hope not.
Yeah, it's difficult.
Yeah, I don't.
Sine is the motion.
I'm not sure actually. So this is the wave equation, as usual, with. So V is yeah. Okay, let me write it like this. And also, I'll write it again. This is sorry.
That's true.
This is the 3D wave equation. Okay, this is the yeah. Okay. Okay. So in the notes he writes this. It's the same thing, of course.
What's the triangle?
The triangle, very good question. This is called sometimes okay, another
Upside down triangle.
I'll write another sometimes they write it with a capital delta. This is the same as this. I don't like this personally. I actually like this better. This is called the Laplacian. So this
Fancy.
is So
Upside
this is
down
the-
and right side of triangle.
this is an operator, a differential operator. That's just it's just the derivative in all directions.
Okay.
So because del
Yeah.
with no squared is just this is just a vector with this, and this. Remember we took the gradient of a function?
Yeah.
It was like the math
Yeah.
group. The gradient function is just the derivative of the x component and the derivative of the y component, right? And if you square it, that's just dotting it with itself, and you get a scalar. It's not a vector anymore, but it's a scalar quantity. It's called the Laplacian. So all it is this is the wave equation in one dimension. It's just extending it to all dimensions. So it's actually not that. It looks crazy, but it's not any more complicated of a differential equation, except that it's in more dimensions. It's in x, y, z, and time. But of course, the solutions are ridiculous. The solutions are way more complicated because well, anyway, you'll see. There's things called spherical harmonics, which are just like the so the ones we found with the standing waves, those are harmonics, right? Those solutions, the sign equations we found with the specific we had to solve for the quantization condition with the k. So we defined it it's n pi over L or whatever. Those are like I guess you call them linear harmonics. They don't really call them. They should. That sounds cool. They should call them that, but they're not. They're called linear harmonics. You could do this in 2 dimensions. The 2-dimensional Laplacian is just this. Okay, the 1-dimensional Laplacian is just this. This is literally the 1-dimensional Laplacian. So 3-dimensional is just this. Okay, you could have a 5-dimensional. You could just put it in many. I don't know why you do that, but you could. Yeah, you could put it in.
Butchered the spelling.
I mean, you could write it. Well, I'm not gonna want to. But
Thank you.
oh, you want to know how to spell Laplacian?
I was wrong. Okay.
There's actually a really cool. Well, I don't think we'll get to it in this class ever, but there's a cool thing in special relativity called the D'Alembert operator, which is my favorite part. So this is actually. So sometimes they write this as this. Now, again, like as I said, I don't really like that because it's a little confusing. This is called a delta, right?
Yeah.
It's a capital delta. This operator is called a nabla. It's another thing. Don't trust me; it's a real thing.
Okay.
This is so this is called a nabla, and this is a capital delta. And I'll make this quick. But in special relativity, there's a thing where you need to take essentially this operator, but you need to take it in. It's called a Lorentz covariant way. It just means that you need to take it in a way that sort of works with special relativity, which has space and time sometimes interchanged depending on your velocity. So the geometry is not. This is like a flat type of thing. But if you put like minus signs here, you could have like a different type of geometry. And the geometry of the world that we're living in is a 4-dimensional space called a Minkowski space. Anyway, the operator looks like this. So it's this. It's d dt squared minus this. So you could write it all out, but it's just this with a minus sign. But it's not just like you add time. You actually add time with a different sign. And the reason is, anyway, you'll see at some point. But this is now the cool part. Now that's not that cool. I mean, it is, but it's not. The cool thing is they use a box, which I think is so funny because it's another time. So it's like instead of a triangle, they use a. Anyway, I thought that was really clever. So this is called the D-Allen version. What's that?
It's another line.
Yeah, because it's four because there's time and it's four dimensional.
So
Anyway,
excited about that.
it's just I thought that when I saw that I was like that is genius. Because someone saw the triangle, which is just a delta. It's not like supposed to be 3 or anything. It's just supposed to be a triangle. But then they were like, let's just, if we add another time dimension, make it a square. That makes perfect sense. Anyway, unfortunately, there's no higher. If there was higher dimensions, you could make like a pentagon or whatever. Anyway, no one does anything in 5 dimensions. So, okay. So I'll. That's called a. I'll write that. It's called a D-Allen version.
I knew you were making stuff up now.
That's the no. I seriously. That's the box.
Box.
Which actually is incredibly important. It's actually called box. That's what they call it. Like if you say box of, I won't write anything. But you say like box of phi is something 0 perhaps.
You're so jazzed about this.
It's really well. This is very important in quantum field theory.
Okay. That
This
sounds
equation is
horrible.
called the Klein-Gordon equation.
Sounds like
I would
something
love
off
to see a portion of what you're studying.
Oh, this is
Just-
a class. You
just
can
10
well.
minutes. I
This
would
is
love to see
nothing,
it.
Ryan.
That's on your own time.
That's what I mean. I would just.
This
You
was
could
first
take-
round.
You can take quantum field theory.
That's
if you
what
want
you're
to learn.
gonna give your
They offer it
presentation.
every.
Yeah, quantum-
I'm gonna give my
yes.
presentation on the box now.
The box.
Yes, you could.
It's
a great operator.
Understand it.
You'll have to do the box.
Moving on.
Anyway,
Gotta be an expert, but.
actually. Well, anyway, okay.
He asks you one question. Defer to Keegan.
Oh, actually, that's cool. So I just realized. I already knew this, I guess, because I hope I already knew. This is a quantum field theory thing. It doesn't really matter too much, but it's not a quantum field. It's just a field theory thing. It's a relativistic field theory, and you can see that this box of phi is 0 is actually this minus this equals 0. So it's just this wave equation with v actually has to be. I didn't write it, but it has to be the speed of light. It's a whole thing. It's when you write the dt, you have to put 1 over c because it's for dimensional reasons. But that's actually kind of interesting. It's literally just the 4-dimensional wave equation, which is true. If you solve it, you'll see that it actually is. But anyway, okay. Let's just go back to other things. So anyway, so this here is the velocity of the wave, okay? And you can, I don't know of a good way why you could see that, but that's where it is, which also means it's here squared if you move it over. And so this for the there's in the notes there's a huge derivation of this. I don't remember if he said it in class, but there's like a huge derivation of this, which is interesting. It's like, whatever. This is the answer. So this is the velocity squared. That means that the velocity, and this is again talking about waves in bulk. I guess in one dimension in a bulk, which is sort of weird. Is b over square root of b over rho naught. Rho naught is the density of the material fluid, and b is the bulk modulus.
So if you're doing how much faster or slower sound travels in water than air, is the B just different for water and air, or is the P different too?
Yeah, this because the density. This is the density of.
Oh, okay.
Right. So water is much more dense than air, of course, right? But the bulk modulus might be different too. I have literally no idea what the bulk modulus is in anything. So you would have to. You could look those up though, and you could just see. I mean, we know. Well, we don't know.
But like the bulk modulus, you can just like look up. You don't have to calculate.
Yeah. No, I don't even know how to calculate it. I'm trying to remember if there was an.
That's just like a number.
I don't think you can. I think you have to look it up
Okay.
because.
And then the
It should
density
be-
you just look up.
Does you yeah? So you would look up these.
And then the faster V is which one is?
Yeah. So which one do you think is going to be
Travels.
faster? Sorry. Okay. So the
Water.
question is, waves are going to travel faster in air or water. Now, of course, don't think about this. If you think about this, you can get it, but I don't. Like, in terms of like what the wave's actually doing in space. Like how waves travel. I mean, we know on a wire, it's not like we just have a bunch of separate harmonic oscillators and they're just doing things. We can talk about waves. It's actually moving because the points, like if we talk about like a string, the points next to each other on the string are actually like influence each other. If this one goes up, this one kind of is dragged up too. That's the whole point of waves, is that there's things that are connected by, if you move one, you're moving the next one a little bit. So in air, we have like a bunch of air molecules, right? And like if a wave comes through, that's like a bunch of these are gonna start, moving this way and like shaking or whatever. And they hit another air molecule, right? And this one just starts shaking the same way. And then of course the other ones lose the energy because they give it and they stop moving. So essentially you get like this wave that sort of travels through, and later it's at this point. Now in water, of course, if we just now forget about bulk molecules, I don't really even know what that is. So if you think about water, in water, the molecules are like much, 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 much closer together. They have to be because it's a liquid. Well, they don't have to be, but they are because it's a liquid. They don't have to be because I assume there's some liquids that are denser than some gases, but whatever. There's something about molecules and hydrogen bonds or whatever nonsense that makes it so that in a liquid, yeah, things are much, much closer together. And so how do you think the wave is going to travel through this? It's going to be faster, yes, because just because there's less distance between them. You don't have to it's not like this one has to hit the next one. They're right next to each other or whatever. So they're sort of automatically, it's sort of like a steel rod or whatever versus a rope. Like a rope, if you or like a slinky, well, okay, let's say a rope. Like a rope, if you make it really tight and you shake one end, you can see the pulse travel. But a rod, I mean, you can't see any, if you hit it, the whole thing is going to start vibrating. You cannot see, it's incredibly fast. I mean, this is one of the things that this completely sounds like it's off topic, but it's a little relevant. People ask about special relativity and how the speed of light is the fastest things can go, right? People ask, well, what if you just had a big, people always try to come up with examples where something goes faster than the speed of light, right? Of course, that's sort of an easy thing to try to imagine, and the answer is always that if something's wrong, you're wrong, it's impossible. But what people say is, what if you just had a big rod, like a rod that's a light year long, and you just shoved it? Couldn't you just communicate? You could vibrate it so that it makes a pulse or whatever. So you could send information or something faster than the speed of light, because that's also one of the things, you can't send information faster than the speed of light. And you can't. But the answer is because when you push, if you had a big rod, when you push on a rod, the other end doesn't move at the same time that you push it. The other end moves when the sound wave gets to the other end. When you put, if you have a big rod, if you push on a rod, what you're doing is giving the part you're holding a sort of slight nudge, and that information is being traveled, and that's why the end moves. So the end actually moves. So if you compute the speed of sound in a big rod, that's actually how long it takes for the other end to move when you push it. So at some point, it's a little bit compressed, right? If you imagine now, of course now, it's a light year long, let's say. The speed of sound in steel is, of course, much less than the speed of light. But if you imagine, let's say it's the speed of light, if you push it, it would take literally a year for the other end to start moving, and in that time, it's actually kind of compressed, right? But that's what sound waves are. It's slightly compressed, right? Usually, sound waves, we don't have enough energy to really compress things that much. It's just sound, but yeah, that's sort of all, So it's not just sound waves in water. It's also just anything that travels through any material, right? When you move it, for example, or any sound, or hit it, or do anything, that actually is the way that materials kind of act as one body is actually, they're not really one static thing. They're actually a series of sound waves that, of course, have a huge amplitude because they move the whole object or whatever. But and they don't really oscillate. They just make it's like a pulse. But anyway, hopefully that was a little interesting. I don't know. Anyway, so that's a you sort of don't think about that as speed of sound. You think of sound as okay, there's a certain type of wave that travels through, but any wave that travels through any object is actually a sound wave. I mean, it's sort of it's operating the same. You might not want to call it a sound wave, but it's operating the same way. It's layers of molecules are communicating with the next layer. And of course, if they're much closer together, so steel has a much higher speed of sound than air, because they're packed. The molecules are packed close together. They're bonded. The solids are bonded together in some sense, and so it's sort of much easier to communicate or to send pulses through compared to gases where they're not actually bonded at all. But you sort of some gases might be so thin that you can't hear really at all. So, like in deep space, there's hydrogen around. It's not like there's a complete vacuum. There are some hydrogen molecules, but it's so scarce that you actually might literally not be able to. There might be so few that you can't actually send any pulses through. Like even in like intergalactic space, it was like the least, the most close to a vacuum place in the universe that we know of is like there's like 100 hydrogen molecules per square inch, which sounds kind of like that's kind of a lot. Like that's not that much of a vacuum. You'd think it'd be like one, but no, it's but still that's like basically a vacuum. Anyway, what were we talking about? Sound. Yeah, speed of sound. So apparently it's like this. Now, once you plug it in, it starts to be less interesting because it's just a number, but you should hopefully get that the speed of sound in water is much higher than air. I think it's like 5 times higher.
For the question that's asking about the increasing its fundamental, what does that mean?
Does it say fundamental?
Increase the frequency of its fundamental by a factor of 1.5.
Yeah, so
what do you have to do to
that's
adjust
n equals
tar
1.
string? Oh.
Yeah, so that was like we the wavelength for n equals 1 was now I forgot, n over 2L or something. Is that right? And then frequency of 1. Sorry, this is over n. Frequency of n was oh wait, no, sorry, it was 2L over n, right? Oh, I forgot. 2L over, I think it was 2L over
Yeah.
n. And then, therefore, the frequency was NV over 2L. Yeah. So this is the frequency of, so the fundamental just means n equals 1.
Okay.
Whenever they say fundamental, they mean n equals 1. So that when they say harmonic, you should be careful. Generally, they just mean, if they say second harmonic, you can assume it's n equals 2, I think. I would be careful about what they mean. But when they say fundamental, it always means n equals 1. So the fundamental frequency is the frequency V over 2L in this case. If I did everything right, you should look this up. But I'm pretty sure.
So it's like increasing the frequency. But what's the factor of 1.5? Like, where does that?
Well, that just means if you have f of 1, fundamental frequency is V over 2L, how can you increase this?
So I'm multiplying it by 1.5?
Yeah, but it's just a function of these things, so you would have to change, you can't change 2, right?
Oh,
You can
so
change V and you can change L. Yeah, that's what they mean. So how would you change V? Or what's V? V is the speed of sound in the, I should say the speed of the waves in the guitar string, which is the speed of sound in the guitar string, but I don't want to confuse it because it's not the speed of sound of the air where you hear it. Okay, that doesn't actually matter at all for these things because the air is just going to vibrate wherever the string did. It's not going to care about that. But yes, you could change V, but you could also change, of course, L is the obvious thing to change because when you hold, that's literally the sort of, that's what people like. If you hold the guitar, the whole point of playing any instrument is to change L. That's literally what you're doing. When you put your finger on there, you're making a new node that you're changing the length L. So therefore, that's how you do it. Usually, you can't change the velocity of the wave in the middle of. Well, actually, you can because the velocity is exactly it's a function of tension. So velocity. So this is from equation that looks exactly like this, but it has T over mu. There should be in the book, they better have a derivation of this. What's that?
What is mu?
Yeah, so mu is the density. So, okay. Actually, Hold on a second. Huh. Okay. I'm a little bothered.
Well, the density of the string doesn't change. You just
No.
If you bend it at one point, you're not changing L. You're changing the velocity
Well,
based on tension.
that's all. That's true.
Okay.
I wouldn't say you're not changing mu though. But hold on. Let me. Okay. I'm a little. Okay. I won't be bothered by this anymore. I'm changing mine. This is the velocity of for a string with tension on it. T is the tension on the string, the force you're holding it with. Mu is the mass density. So it's the mass per meter.
So if you're stretching it, okay. So yeah, you are changing mu if you're stretching it.
Yes, exactly. So what I was saying about V, how can you change V? Well, of course you could just use a different material. But generally, when you're playing an instrument, you're not going to like unstring your guitar and string it with a nylon or whatever. And like that's kind of crazy. So, but if you change, bless you, if you tune it, if you tighten it, you're of course changing T. That's immediately what you're doing. But you're also, if you tighten it, you're actually pulling in some string, and so it's the same length, but now your mass is actually less. So you're actually changing both T and mu. Now that's a little more confusing because now you might think, well, am I changing them in a way that keeps V the same? Oh, no is the answer. Spoiler, the answer is no. You would have to do some derivation.
Otherwise, your guitar would sound the same.
Yeah, exactly. Otherwise, tuning it would. Yeah, so I guess okay. You know from experiment, I would say. I would call that knowing from experiment.
Still,
Yeah.
my life is working.
You know from experiment that these don't cancel out; they're changes. But yeah, so basically, changing the fundamental, and by a certain factor. Now you have to worry about how the factors affect this, but changing the fundamental can only happen if you change L or you change V, right? Changing L is you do with your fingers on a guitar, for example, or on a flute or whatever. When you like push one of the keys, I don't know.
The keys.
The keys, okay. Pushing the keys, you're making like a hole there, and the holes. So what's that?
You're closing a hole.
Okay. I don't know how to The point is that there's something where you're making it so that there's another open end at a different point, I think. So again, I don't really know. On some instruments, there's you somehow want to make another open end. So basically, it's the same as a guitar where you're making a new closed end at a different position. Whereas with a flute, you're somehow making another open end because, of course, it's open, but it's the same mathematics. Or maybe it's closed. I don't know. I'm not sure. Maybe flutes are closed. Anyway, whatever. The point is that you can do both, and some instruments do both. But if that's changing L, and you can change V by turning the, for a guitar, turning the knobs, the tuning knobs. And I actually have a guitar, and I don't know what any of this is called. I don't really play it, but I play
the only
piano.
reason I know this.
But it doesn't really, you don't need to know any of this. And so then you can, of course, that's changing the tension by a lot. It's changing the mu by a little, but that's probably a good explanation. Is that when you tune you turn the knobs, so you're pulling the string, and you're not actually changing mu by that much. It's very small, but you are changing T significantly because you could make it really tight or really not tight. So anyway, so roughly you could say but you are changing both. In such a way that you are changing the velocity of the waves. You can get to, if it oscillates very slowly, it means your velocity is very small, and et cetera. And therefore, the frequency gets changed.
Okay.
The fundamental frequency. Of course, all of them get changed, right? Because Fn is n times that quantity. So if you change that, you're changing all the frequencies. And actually, they always have the same ratio. So that's really important. That's why when you tune your guitar, you don't have to it's not like, oh, wait, now I have to use this fret. All right? You don't have to use this fret for, it's not like the notes mean anything different. The notes are all identical, no matter how you tune it, right? The notes are all identical ratios. That's what I meant. Okay, I guess that's not obvious. Never mind. I thought it was going to be more obvious. It's not really obvious that that's true because it sounds off either way. But the ratios, if you put your finger halfway, it exactly has halfway means that you're at n equals 2. And so you get, L goes to, okay, never mind. This isn't as easy as I thought. the point is that the ratios are the same, and that's because the frequency is just n times a constant, assuming these are fixed. This is a fixed thing. N times a constant is just a multiple of that. So your frequencies are always multiples of that thing. Yeah. Does that make sense?
Yeah.
And then there's all these music stuff you can talk about, like if you double the frequency, it's like an octave or whatever, and it's, you know.
So this
Very
one
good.
asks.
And there's all these weird ratios. There's actually these weird things about when you tune. Well, okay, I won't get into it. There's a YouTube video that you should look up, which is actually really cool. It's on the channel Minute Physics. Which, does anyone know about
No,
Minute Physics?
yeah.
Okay. He's a postdoc, Canada or something like that. Anyway, Minute Physics, and then if you look up tune a piano, there's a video on how it's called You Can't Tune a Piano. But it has to do with this and how these are all rational numbers. Okay? So it's not that important that these are rational numbers actually, because these are just measurements. But the ratio between any two frequencies is of course a rational number. It's an integer. Well, okay. It's not an integer, it's a rational number, because if you divide f of n over f of m, you get n over m. That's of course a rational number. But if you try to tune like the ratio between two, like like two half steps on a keyboard, or I guess on anything, if you do the ratio between two half steps, and you keep doing that, the ratio over and over again to get to one octave, you want to get to double the frequency after one octave, but there's 12 half steps. So what fraction, right, what ratio of a half step to the previous half step can you do such that when you take it to the 12th power, because that's what you do when you iterate it, right, you get 2. Well, there's no rational number that you could, it's the 12th root of 2, right? Because what number, so if a half step is like, a half step is like this to this, so on a keyboard or whatever, right? And you get, whatever, dot, dot, dot. This is a half step, and so you want the ratio of frequency 1 to frequency 2, I'll say, to be some number such that then frequency 2 to frequency 3 is the same. Of course, it's half step. Half step means the ratios have to be the same, right? So frequency 2 to frequency 3 has to be the same ratio. Frequency 2 to frequency 3, dot, 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 such that frequency 1 to frequency 12, which is an octave up, has to be 2, right? Well, frequency 1 to frequency 12 can be written as frequency 1 to frequency 2 times 2 to 3 times 3 to 4, right? Does that make sense?
Mm-hmm.
Like, if I can write this number, frequency 1 to frequency 12, which is 2, has to be 2 by sort of requirement, is equal to frequency 1 to frequency 2 times frequency 2 to frequency 3, right? Of course, these just cancel, but,
1 to 3, yeah.
3, 4, all the way to 12, right? 11 to 12, and the requirement, of course, the requirement of the fact that these are all, oh, I didn't mean to erase that. Whatever. The requirement is that these are all the same number, because of course, if they're all, these are supposed to be half steps, so their half step is to be the same number. So I have some number, I'll call it this thing, pound, to the 12th power, because there's 12 of these, is 2, because this has to be equal to 2. Well, therefore, hashtag or whatever, is 2 to the 1/12th, right? This number is not a rational number. So how can I possibly tune these things, right? All the frequencies I just saw had to be rational numbers in relation to each other. So this number is not rational. So you actually can't tune a piano using the sort of standard methods. This is called equal tempered. So this is a real music thing. If you actually tune each half step to be exactly the same ratio, if you tune it like this, you have to use a computer, right? And you actually have to approximate at some point. But you get, it's called equal tempered. But when you tune real instruments, like when I used to tune them, they usually they just get close enough. Who cares? But it was, it's not actually a real, you can't actually use sort of the real ratios to tune it, because no ratio is equal to this. Anyway, if you look up this video, they say it. He says it better than I do. But it's really interesting.
The one with like plotting the function of tension with
Oh, yeah,
the
sorry, what did that say?
wavelength?
I read it real quick and I forgot.
if you were to plot as a function of tension of the string T the wavelength of the fundamental standing wave in a given length of string L, what will it look like? Is it just like straight?
Well, if you plot over the tension, well, we know that the fundamental wavelength was, I don't have it anywhere, 2L over N. I know I keep forgetting. Yeah, 2L over N, okay. Well, yes, so remember the frequency, as we saw, had V in it, and V has tension in it. But this, if L is fixed, okay, and N is 1, the fundamental frequency is 2L. If you say the length is fixed, no other thing can possibly change that. Right? If you change the tension, well, you're not changing L, they told you. So you cannot change the fundamental frequency. So you're exactly right. It's just a flat line. In other words, the fundamental frequency is independent of the tension. The reason that this is not a stupid question, it would be a stupid question if they just said like something completely unrelated. But if the fundamental frequency is related to T, as we just saw, we just saw it's 1, so N is 1, times V over 2L, right? This is the fundamental frequency. Well, this, if we replace V with T over mu, now if we plot this, we would get something. We would get like a square root of, something like that. It's like a square root of T, because we get square root of T over square root of mu 2L. Those are just constants, I guess. Or just assuming those are constants. So you get something like a constant times square root of T, which is like that. So the reason that they're asking that question is because the frequency is dependent on the tension, but because it affects the velocity of the waves, therefore it affects the standing waves, of course. But the wavelength is not dependent on the tension. The wavelength is only dependent of the fundamental, is only dependent on all of them, all the wavelengths of all the frequencies are only dependent on the length of the string, of course, because they're just, as we saw, we only had to use the thing that I had written here and erased. We only had to use the fact that at the end point, after length L, it has to go to 0. The sign has to go to 0. That's just the quantization condition. So we only use that. We didn't use anything about waves or velocities or anything like that. So yeah, that's a good question.
So for the 9th one, do you just like figure out the speed of the wave and the mass of the rope using the equation it gives and like the equations for like V?
Yeah, sorry, no, I just don't remember the slash. Didn't really read it. I see the third one. Yeah, so pi x over 2 times 18 pi t. Okay, so we know that omega is 18 pi. And we know that k is, if we put it in the form sine of kx times sine of omega t, right?
Mm-hmm.
And k is, what was it, 1/2 or something?
Pi x over 2.
Pi x over 2, so it's, actually, okay, now I'm getting confused. Well,
Third harmonic.
Right, it's the third harmonic. Okay, well, let me just write sine pi x over 2 times sine 18 pi t. Well, we know, oh, yeah, okay, so, so this f, by the way, that I've been using for all these things, f is always in hertz, right? It's not the omega. So we can go from oh, sorry, hold on. There. I know these are right because of the units that aren't really units, they're pretend units, but they're sort of labels. That's what I call, I should be calling them labels. Units are real units, like seconds. This is 1/seconds. This has units of 1/seconds. Those are all right. But of course we can use the labels of this is radians per second. The 2 pi is 2 pi radians per cycle. That's always what it means. Like 2 pi is, that's what 2 pi means. And frequency is cycles per second. So we can kind of see that this has the right units, the way I've written it here. I'm writing this out, all the units now, because I just wrote it the wrong way. And it's very easy to write it the wrong way. But we know that 2 pi can't go over there, because if it went over here, we would have like radians times radians, and that wouldn't make any sense. So we can see like radians per second. So anyway, therefore, omega over 2 pi is f. And so omega was 18 pi, which is 9, right? So f is 9. Do they say the length at all?
No. String under 250 newtons of tension.
So they say the tension. Do they say mu anywhere, like the mass density? I mean, we don't have to have it. We could. No, well, we know because we don't have to. Well, okay. So F is 9 hertz, which is very low. Whatever. And we know that the graph looks like. So at t equals, whatever t equals.
Does it matter that there's a 0.2 in front of the first sign?
There's a 0.2 here.
Mm-hmm.
No, this would just be the amplitude.
Okay.
Yeah. So for all of these things, we didn't really care about the amplitude.
Okay.
It was just like, if we're talking about the thing where we add the waves together with the beats, it kind of does because if we had different amounts, we would have to add them up more carefully.
Okay.
But for the most part, we can kind of ignore it. It should be in the answer, of course, but can I see it again, actually? So it represents the third harmonic. Oh, I see. So what we want, so it's pi x over 2, and this is the third harmonic. And so therefore, the frequency, which is 9, well, we know that the frequency looks like this, n v over 2L. And n, now we knew this was the third harmonic, which means n is 3. Again, I'm just assuming that. Let me just look, actually, because I hope I don't get your book. Let me just see if they say. I think they use the convention that the first harmonic is just the fundamental. Huh. Okay, I don't really see it anywhere. Okay, they say n equals 2 harmonic. Okay, I'm gonna assume they mean n equals 3. So this is n equals 3, therefore this is 3v over 2L. And therefore 3 is v over 2L, right?
Mm-hmm.
So we got this, so I erase all this nonsense in a way. So that's interesting. So now we know that, okay, the thing that's bothering me is that we don't know the length. We know that looked like sine pi x over 2 times something. So we know it should kind of look like this, right? After a length L. And therefore, if we know it looks like this, that means that, oh, okay, I guess we can find the wavelength. Well, the wavelength we know is 2L over n, and it's the third harmonic, so it's 2/3 of L. Okay. And the wavelength is related to k, so k is pi over 2, right? Because it's just the rate. And the relation between k and the wavelength is actually the same as that relation up there. K was, K is 2 pi lambda. Is that right? No. K is 2 pi over lambda. I think that's right. The units work because this is 1 over meters and this is 1 over meters. This is in radians per meter, right? That's K is always radians. We know that has to be radians per meter because it multiplies meters and it has radians because it's in a sign. So it's radians per meter. This is radians per cycle, and this is meters per cycle. Wait, no. Yeah, so, okay, something's wrong. Wait, is that right? This is, okay, radians per cycle. And this is meters per cycle. Oh, okay. So we get radians per meter. Okay, that's fine. Good. So this is right. Right, because those cancel and you get radians per meter. Okay. So therefore we can write k, which is pi over 2, equals 2 pi over lambda. Okay. And then we get, therefore lambda is 4, right? So move the 2 over, we get 4 pi, and then the pi's cancel, and move the lambda. So lambda is 4, and therefore we can find L. So therefore 4 equals 2/3 of L. So L is 6. 4 is 2/3 of 6. And, okay, so we have L is 6, and now we can plug in 6 here. So 2 times 6 is 12, times 3 is 36, is V. Ooh, okay. Now, I hope I didn't do anything wrong. I don't think I did. So all we used was the relation between the wave quantities, which are the wave quantities I would call lambda and f. So these are, okay, I won't write it. The wave quantities I would call lambda and f, because those are properties of waves that just, you don't have to know anything about the functions, you just have to know about the waves, right? But the inputs are k and omega, which are, I would call them like mathematical quantities, because they're all in radians. And in real life, in musical instruments, no one cares about radians. Who cares? It's only because we use sine functions and they just happen to take in radians because it's how they are defined. But it doesn't really matter. Yeah. So we had to convert between them using these things, this and this. And if we're given the explicit function, of course, we have omega and k, and we could find, therefore, we could find f and lambda. But of course, we already knew f by the fact that they told us it was the third harmonic. And we know that for a fixed endpoint wave, the third harmonic has a frequency that's given by whatever, and we get something. And then we also could, again, the same way, we could find the wavelength of the third harmonic. And therefore, now the reason we had to know those things in different ways is because there's many unknowns like L and V. So if we had two things that we found in two different ways, we could actually solve for the two unknowns which we have, which are V and L. So that's what we did. Does that make sense? Now to find the tension, which I think, did they ask that
For
too?
the mass, they give you the tension.
Oh, okay. Well then, of course, we could just use this. There you go. I was going to say, I thought they asked for the tension, they didn't say anything else, but that's good. Because V is radical T over mu. This is just for a wire under tension. That's standing waves for a wire under tension. This is very similar to the, now, okay, oh, actually, okay, this is the same thing. So remember when we talked about bulk modulus? Bulk modulus is kind of like a pressure. Did I say something like that, or a tension? Did I say that? I honestly don't remember because I don't remember if that's true, but I believe it is because in the velocity of things in air. So remember when you have like the open system. Of course, if it's open, you're not going to have like a wire because a wire is not open. But a wire is, well, you could, I guess, have it. Well, no, you couldn't. It doesn't make sense. So, but for like air can easily be, unless you seal off the ends, air can have open, which just means that the end points have the maximum oscillation that they can have in the system. And we know that the velocity by, some derivation that's in the thing looks like that. And the thing that was, so I remember like 20 minutes ago I said something was bothering me and then I said I changed my mind. Well, I didn't really change my mind. I just stopped talking about it. But what bothered me was that this is the velocity of sound in air. And on the bottom, you see we have the density of air, just like we have the density here, right? And on the top, we have a tension, and I was a little worried that this B was not really tension. But I believe it is, right? Because that's kind of what it's like, a stiffness. Remember when there was an office hours a while ago where I was talking about like if you, like Boyle's law, if you compress something slightly, how like sort of stiff is it almost? That's essentially like a tension, but for 3 dimensions, right? Sort of how does the pressure respond when you compress the volume? And that the answer to that is the bulk modulus, just like the answer to that in the other version was, in the one-dimensional version, was the Young's modulus, which was kind of like a tension. So I'm sure you could write this, it might be slightly different, but you could probably write it in terms of Young's modulus. But anyway, so they just happen to, because they've already told you about bulk modulus, they used it here. It's probably some, okay, no, that's fine, I guess. So anyway, the bulk modulus is sort of like, you can think of it like a tension in 3 dimensions. It's sort of like how, because if you imagine you put the air under a lot of pressure, right, and you increase the density, you should have different amounts of, of course, waves therefore would travel faster through them, just like we were talking about. Waves travel faster if the molecules are closer together. And if they travel faster, that means that standing waves, of course, because remember, standing waves are one wave reflected, and if they're going faster, it messes up all the frequencies, so you would have different frequencies and stuff, and that's why there's a V here, right? But the reason there's a V in the frequency thing is because you couldn't have standing waves if the reflected waves traveled faster or slower or whatever, because you changed one of these things or one of those things in a gas or fluid, I guess. Then, of course, the standing waves would be different because the incident and reflected waves would go at different speeds, and therefore you would need to sort of tune them a little differently to get them to perfectly sync up so that they're standing waves, and therefore you would need you would get different frequencies out of it. Because remember that it's not just you can't just get any frequency out of these standing waves. As we saw, you can only get there's an n here. N is an integer. It's not any number. It's only integers. You can only get certain values. And so you saw that if you turn any of these things, sort of the tension or any of these variables up, you're messing with usually the velocity of the waves, or the length there. Of course you could get, mess with the length, you're of course gonna mess with how big your waves are. And if you mess with how big your waves are, you're messing with the frequency, obviously, and the wavelength. Okay.
And then mu is just m over L.
Mu is, so if they told you the mass, mu is, if they told you the total mass of the wire and the total length of the wire, it would just be m over L, yeah.
Okay.
They might say, like, it's made of this diameter steel, and they give you the density of steel, and you just, whatever, you would find the mass. It's the same thing, I guess. You would just find the mass.
Okay.
It's literally just the total mass over the total. It's just like this is m over v.
Yeah.
Like density is m over v.
So you would like use all this to solve for mu and then divide it by the 6, the length, wherever that was.
Oh,
Or is that not it?
yeah. You mean if they told you the density of steel or whatever? And
Well, so you just
Because
solve
it's
for
asking.
you have
Oh.
L and you have mu now,
Yeah.
so you just solve for M.
Just making sure.
Wait, sorry. Did they ask you the mass of
Yeah.
the wire?
Yeah.
Oh, sorry. I thought they asked you for mu. Yeah, but then
No.
yes, exactly. You're
Okay.
right. This would just be m over L. Yeah. So
Okay.
then you would do all
I
that.
just wanted to make sure.
Yeah. Thanks for. I thought they were asking for mu. Right, because we have L. Good. That's a good question. That problem in the book is very good. I like that.
I think that's the first.
I feel like that's
Is it
rare.
first?
No, I actually do. I mean, it might have been just. It's
Oh,
probably
almost.
just from another book.
Wow.
No, but it's actually. I mean, like this type of question is in every book. So.
Wow.
If you've taken physics before, I don't know if you've ever taken anyone's take, but if you've used mastering physics,
Mm-hmm.
okay, it's the worst thing ever.
Oh, it's
of course,
worse
but
than
it's,
Blackboard.
yeah, it's worse than Blackboard. It's made in like 1989, when the first internet. Anyway, whatever. It's awful, and you type things in, and then it says it's not right because your answer doesn't have the right. You put an O instead of a 0. Anyway, whatever. So anyway, there were awful problems just like this. Like this would be a problem, and it would just be one thing, and you'd get like 3 tries, and you have to do it online.
Oh,
It's
oh
the
my god,
worst
I
thing.
had to do that for physics 1.
Yeah, was it
I
mastering
remember
physics?
Yeah.
Or Pearson mastering.
Pearson-
Yeah.
Pearson mastering, yep.
Yeah.
I had to do this.
Oh my god.
And you have to buy the textbook so you get
Yep.
the code.
Yeah.
Yeah.
Then you have to
Yeah.
pay for the subscription to
Mhm.
Pearson.
That's
I don't think I ever opened that book because it was just the work. Because why would you look? Like you literally Google everything.
I had
It's all
to.
there.
I got a free
Chegg.
semester at Chegg once.
I was gonna say check.
Yeah.
That was a
Literally
and then,
Chegg.
they got me because I paid for it.
Yeah.
Yeah, I paid for it.
Yeah, me too. I think I still am. Forgot to end it.
Figure it out.
You should end that. That's like $14 a month. Or it used to be $14.
Oh my god,
It's probably like 20 now.
Oh, I think
that's
I ended
ridiculous.
Oh yeah, they get you.
Yeah.
It. They do.
Is that more than
It hasn't showed up on my.
Netflix is climbing to
Credit
20
cards.
soon.
What?
What?
Yeah. You haven't heard that?
No.
No.
Well, they don't make profit.
They're
like,
not
'cause they
making
don't
money.
have
Oh,
ads.
no, I'm
they're
sure
gonna,
they don't,
They're gonna
yeah.
like cut back on the sharing thing, even more that they already have. But
God.
But I mean, that's the only reason people get Netflix is because there aren't commercials.
Right.
I hate that. Is it Hulu?
Hulu,
Yeah, Hulu.
If you have Spotify, you get it with commercials.
You get it with commercials. If you pay the maximum price for it, it has commercials.
What?
There's literally no amount that you can pay to not have commercials. Yeah. The most
Yeah.
there's like a lower price and a higher price, and the higher price still has
They're
commercials.
the only ones that have Fox, but like, what's on Fox? I don't watch anymore.
I don't know.
I
It was a
use
big
my
deal.
old
Oh,
roommate's
American Horror
mom's Hulu.
I'm not a fan.
I don't watch like networks.
You know what you should watch? Sorry,
Mad
if anyone has any questions, let me know. But I've been watching Mr. Robot. Have you seen Mr. Robot?
No.
It's a fantastic show. It's like really good. Anyway,
The prequel to Game of Thrones is coming.
yeah, I saw the House of the
Ooh.
Dragon.
Yeah, it's coming. And George R.R. Martin is writing it.
Yeah.
Yeah.
I saw
Thank
that.
God.
I hope those people aren't making it
They were
again.
horrible.
I know
the
they're
last
awful.
season.
They're really terrible.
Oh,
This is him
That
saying
was-
sorry.
yeah.
So he's gonna write
You
it.
better.
Yeah.
Jump out a window.
That was
You
tragic.
hear from the book in like season 2.